Welcome to another lesson in Math 4 Honors. I'm Kirk Weiler, and today we're going to be looking at percent challenges. I always like to do a day on this, even though percent is work that students have been doing for many years. I think it's really important to make sure that you've got some sort of tricks up your sleeve for really understanding what's going on. See, when we think about a quantity increasing or decreasing by a constant percent, what's really important is to understand that that's a multiplicative process. And when it happens repeatedly, we summarize that multiplication with exponents, right? So some people get very confused because, when they see something like it's growing 5% per year, how much does it grow over 10 years? They say, right, it must be growing by 50%, 5 times 10. The problem with that is that then treats percents as an additive process. And so if you do it repeatedly, you summarize it by multiplying. But that's not the case. So today we're going to really kind of get into that. We're going to look at how we can frame or think about percentages and repeatedly applying them in terms of exponents, and likewise how we can sort of go in the reverse by thinking about roots. Anyway, let's start off with hopefully a very easy problem. In exercise number 1, we're told that a population of wombats is growing at a constant percent rate. It tells us that the population on January 1st is 1,027, and a year later 1,079. We want to know what the yearly growth rate is to the nearest tenth of a percent. This is certainly a problem you should be able to do at this point in your mathematical careers, so pause the video and get me a percent. Alright, let's go through it. We want to know the percent that it grew. In order to know the percent that it grows, it's first helpful to simply know how much it grew, right? So how much did it grow by? It grew by 1,079 minus 1,027, or it grew by 52 wombats, right? Now what we need to know is, based on how many we began with and how much we grew, what percent of what we began with did we grow by? Well, that's easy. It's like getting a 52 out of 1,027 on a test. Don't get me wrong, that would be horrible. But of course that would give me my sort of percent as a decimal, and then if I want to know it as the straight up percent, I multiply by 100 and I get 5.1% to the nearest tenth. Now another way of thinking about it is to do something like this. You could just simply ask, how much would I have to multiply 1,027 by? What would I have to multiply this by to get me up to 1,079? Right? If I solve for x, which is clearly 1,079 divided by 1,027, I would find that I'd have 1.05063. It's just messy, right? The idea, though, is that I would be multiplying by this number, 1.5063, which hopefully then tells you that you can extract the percent by looking at this, 5.1%. Now, exercise 2 says, by what percent do the wombats from exercise 1 grow over a decade? Round your answer to the nearest whole percent. So the key here is understanding that every year, because it's growing at a constant percent rate, every year we're going to get to multiply by 1.05063. All right? Now, what we'll do is we'll use that 5.1% from the last problem. So after 1 year, right, we multiply by 1.051. After 2 years, we've multiplied by 1.051 squared. After 3 years, by 1.051 cubed, etc. So after 10 years, right, after a decade, we will have multiplied by 1.051 to the 10th, which gives me 1.644, etc. Now, in other words, what it means is that if I wanted to sort of immediately go from year 1, or year 0, if you will, to year 10, I could multiply by 1.644, etc. But that means that over a decade, my population is growing by, whoops, definitely wrong place for the decimal. My population is growing by 64%, right? So by repeatedly multiplying, we get an exponential quantity, not a multiplicative quantity. See, a lot of people might say, oh, well, if you're getting 5.1% per year, and you multiply by 10 years, you should get a 51% growth rate. But you don't, because that would be saying that we add using percents, and yet we don't, right? We multiply. Let me go back and just really quickly erase what definitely doesn't look like a 5. And in fact, notice that this growth rate is actually significantly higher than what would be predicted, and that's because each year, right, we're getting to multiply a larger number by 1.051. So keep in mind, it's all about multiplication, and repeated multiplication then turns into exponentials, or exponentiation. Okay, exercise 3. All right, let's stick with the wombats. You gotta like a good wombat. It says, assuming their growth rate is constant over time, right? What is their monthly growth rate to the nearest tenth of a percent? Assume a constant sized month. All right, so 12 months in a year. That's simple. I want you to think about this for a second. I want you to think about how you could figure out the monthly growth rate if the yearly growth rate is 5.1%. Pause the video and see if you can figure this out. All right. Now, I want to mention the wrong approach. I know that seems weird, but again, the wrong approach would be to say, well, we're doing 5.1%, let's just divide by 12 and get whatever we're going to get. That is the wrong approach. Big circle, cross it off. What I would love is if some of you realized that you simply go the opposite way. In other words, right, after a decade, we got to multiply by 1.051 to the 10th, right? But after a month, right, we'll go in the opposite direction. It would be to the 1/12th. This would then result in an answer, and of course you got to do this on your calculator, of 1.0041, etc. Got to be careful here. That then indicates a 0.4% monthly growth rate. Now, if you're confused about this, one way to look at it is you could say, well, I don't know, I could let m be sort of my monthly multiplier, right? And what I would know is that if I took m and I raised it to the 12th, I would have to get my 1.051. So this is if m is my monthly multiplier. I don't want to call it my monthly percent rate, because that would be sort of 1 plus m. But anyway, my monthly multiplier. It's all about multipliers. Now, to reverse this, to actually figure out what m is, I would raise both sides to the 1/12. All right? So this is really kind of cool. Right? Typically in percent growth problems, what you know is you've got some unit of time. The day, the week, the month, the year. Most often the year. And you then know the growth rate for that span of time. I'm growing at 2% per year, or I'm declining at 5% per year. Then the question becomes, well, all right, if you repeatedly apply the year, so you go to a time span larger than the year, well, then you're going to be raising it to this exponent that's greater than 1. On the other hand, if you have to go backwards, right, then you're going to do a root, or let's say a fractional power less than 1. Okay. So let's take a look at number 4 and see if you can figure this out quickly. If a population was growing at a constant rate of 22% every 5 years, then by what percent is it growing for every 2 years? Round to the nearest tenth of a percent. I would love it if you were able to do this with a single calculation. If not, work through it in multiple calculations, all right? But pause the video and really think about what we've been talking about. All right, let's do it. Some of you probably figured this out, how to do it all in one calculation. I'm going to write down the one calculation, and then we're going to talk about it. So I get to multiply by 1.22 every 5 years. if I want to figure out what I get to multiply by every 2 years, I'd raise that to the 2/5. That would be 1.0827, etc. Messy number. And that would tell me that I'm getting 8.3% every 2 years. It's not a yearly growth rate, it's a 2-yearly growth rate. That didn't make a lot of sense. So let me explain why the 2/5 power makes sense. Let's say that you just wanted to figure out what your growth rate was per year. Well, that takes us back to the last problem, right? If I wanted to know what my growth rate was per year, and I know what it is per 5 years, then to go backwards, I'm going to raise to the 1/5. So this is per year. And that is whatever it is. You could easily work it out. That would be fine. But keep in mind that what you'd then have is your yearly growth rate, and you would then square that. We've got this beautiful law of exponents that says if we have something raised to a power raised to another power, we can multiply the powers, right? So then we get 1.22 to the 2/5. All right, let's keep looking at these things. Now, everything on the front side of the sheet was a growth problem, all right? Students tend to find decay or decreasing exponential percent problems harder. So let's take a look at one of those. In exercise 5, it tells us that the world oil reserves, the amount of oil that's unused in the ground, are depleting at a constant 2% per year. Whether they are or not is questionable, but I'm going to take some liberties here. What will be the decline in terms of percent from today after 5 years, 10 years, 20 years? We're going to round all of our answers to the nearest tenth of a percent. Now, understand, what will be the decline? In other words, I want to know, after 5 years, what percent less oil will we have? After 10 years, what percent less oil? Okay? If you think you know how to do this, pause the video now and take a shot. All right, let's take a look at it. Now, here's the key. When we model using exponentials, almost universally we are, if you will, modeling what we have left of a substance. Whether it's growing or decaying, it's what we have, not what we've lost. Okay? So keep in mind that after 1 year, we'll get to multiply by 0.98, right? Therefore, we would have lost 2%. After 5 years, we're going to multiply by 0.98 to the 5th. And what we're going to get is 0.9039, etc. That means we have 90.4% remaining. A lot of students go too much on autopilot and they say, that means you've lost 90.4%. No way. No way. We have 90.4% remaining, which means that 100 minus 90.4, we've lost 9.6. Right? That's the actual answer. That's how much it's declined. So I can say, after 5 years, it's declined 9.6%. Now again, if you were thinking about percent as an additive thing instead of multiplying thing, you might say, well, we're losing 2% per year. After 5 years, we will have lost 10%. But not quite, right? Only 9.6%. All right. Now, if you didn't go through the entire question before when I asked you to pause the video now and figure out what percent decline we've had after 10 years and what percent decline we've had after 20 years. All right, let's take a look at the rest of the problem. All right, so after 10 years, very similar approach. I'm going to have 0.98 to the 10th. That's going to give me 0.81707, etc. Right? That means that I had 81.7%. I'm just going to put some air quotes here, remaining, which means I have 100 minus 81.7, or 18.3% decline. So I've lost 18.3%. Likewise, after 20 years, 0.98 to the 20th gives me 0.6676, etc. That means that 66.8% of the oil was remaining, And that tells me that I have 100 minus 66.8, or 33.2% has left. And again, it's always, I think, worthwhile to compare these numbers to like what you would get if you thought it was additive. Right? If you thought it was additive after 10 years, you would have expected 20% to have declined, right? 10 years, 2% per year, 10 times 2, 20. Likewise, after 20 years, you would have thought 40% decline. But notice the declines are somewhat less, and that's because we're taking off a 2% off of a smaller number each time. All right, let's look at the classic. Okay, one of the things that people always talk about when they look at declining exponentials is the topic of radioactive decay. You know, as if a lot of high school students have a lot of experience with that, even college students. Anyway, let's take a look at a radioactive decay problem. A radioactive substance's half-life is the amount of time needed for half, or 50% of the substance to decay. Let's say we have a radioactive substance with a half-life of 20 years. All right, now what that means, right, just to make sure you understand half-life, if I have 500 kilograms of a radioactive substance, after 20 years, only 250 kilograms will still be radioactive. All right. Then, if I have that 250, after another 20 years, only half of that, or 125 kilograms, will be still radioactive. So pause the video now. I bet you can figure this out. What percentage of the substance would be radioactive after 40 years? Did you figure out that it was 25%? If so, then you obviously got the problem right. All right, let's take a look. Get rid of stray marks. All right. Now, a good way to think about this, right, is that I'm getting to multiply by 1/2 every 20 years. Right now, it's very easy here because obviously you know that you've gotten to multiply by 1/2 twice, right? Which gives you 1/4, which tells you you have 25% of the quantity remaining. More generally, right, you will always figure out how many times you got to apply the 1/2 by taking the number of years that have passed and dividing it by 20, right? Because this ratio is equal to 2, we've gotten to apply the 1/2 twice. Take a look at letter B. What percentage of the substance would be radioactive after only 10 years? Round to the nearest tenth of a percent. Pause the video if you need to. All right, this is much trickier. Much trickier, because again, a lot of people will slip into this bad thinking that it is somehow an additive process. They'll say after 20 years we've lost 50%, so after 10 years we will have only lost 25%, so 75% will be remaining. And that's not true, right? The way to look at it is, again, I have 1/2, but here, if you will, I'm raising it to the 10/20s, right? I only get to apply it 1/2 times. I know that seems weird, but so I have literally 1/2 to the 1/2. If you want to think about it this way, it's the square root of 1/2. That ends up being 0.707, etc. So 70.7% remains. What percentage of the substance would be radioactive after 5 years? I bet you'll be able to figure this one out now. Pause the video really quickly and come up with an answer. All right, hopefully you got 84.1%, but let's take a look. Again, the question is, how many times do I get to apply multiplying by 1/2? Well, I only get to apply it 1/4 of a time. I know that sounds weird, right? But that's the whole point of fractional powers. And again, if you want to think about it this way, it's the 4th root of 1/2, but you don't have to. Obviously, you can just enter 1/2 to the 1/4 on your calculator. That ends up being 0.8408, etc. So we'll go with 84.1%. All right, that's our lesson for today. I hope that you have a better ability now to apply repeated percent increase and repeated percent decrease. Remember, right, this is a multiplicative process. To go forward in the process, you're going to be, raising your multiplier to powers greater than 1, and to sort of go backwards in the process, you're going to be raising your multiplier to powers between 0 and 1. All right, decay is especially tricky. Remember that when you do any kind of decay problem, or growth problem for that matter, you're always modeling how much of the substance is still there, right, is present, not how much is left. That you have to then do a subtraction for. All right, let me end there. Thank you for joining me for this lesson. Take care, and remember, until next time, keep thinking and keep solving problems.